Hello and welcome to Talking Points. I'm Dave Kelly, Director of Advanced Media Production at Cal State Long Beach. Today we're going to talk about engineering technology and the advancements that will be coming soon in both aviation and robotics. My guest today is Dr. Praveen Shankar. Dr. Shankar is an assistant professor in mechanical and aerospace engineering. Welcome, Praveen, and thank you for joining us on Talking Points.
Thank you. I'm glad to be here.
Well, there are a lot of developments in engineering technology today, but we're going to start with aviation and some of the things that are going on in that area. And I know that, as with everything else, the drive is to create cleaner machines, and we're talking about aircraft now. And so both the FAA and NASA have been invested in finding technologies with new aircraft designs that will yield aircraft that are more fuel efficient. What are some of the challenges that engineers have to deal with if they want to make a jet more fuel efficient?
Well, fuel efficiency basically depends on how the aircraft moves through the atmosphere. Right? So whenever we have an object that moves through a fluid, for example, when we move our hand through water, we feel some sort of a resistance on our hand. This is the same thing with the aircraft. When it moves through air, it feels resistance, which we call as drag. And larger the drag, the more effort that the engines need to put in for the aircraft to move through the atmosphere. So if your aircraft is more aerodynamic, then the drag is reduced and your aircraft is going to be more fuel efficient. Of course, beyond this, there is also the weight of the aircraft, because depending on the materials that you choose to build the aircraft, the weight may be more or less, which means that the lift that is required to put the aircraft in the air is larger, which again subsequently increases drag. So it's not only just the design of the shape, but also how fast that you're going through the air. And finally, there are a lot of technologies within the engine itself that can make it more efficient. So that affects fuel efficiency.
All right. Well, there is one project in particular that's received the attention and the funding of both the FAA and NASA, and that's a project known as the Aurora Flight Sciences D8 or double bubble. We have an image of that right now that we're showing the audience. And as we look at the Aurora D8, it has what's called the double bubble hull, which is a wider fuselage and also more narrow wings, and the engines are located underneath the tail, above the aircraft, but underneath the tail. Why would those designs be potentially more fuel efficient?
So one thing about the double bubble design is that it increases the surface area of the fuselage. Now, every surface on the airplane acts as a lifting body, which means that it contributes to the lift that counters the weight of the aircraft. With the fuselage being having a larger surface area, like the double bubble design, the fuselage itself acts as a lifting body, which reduces the size of the wings required in order to produce the total lift. Now, how does this help? Well, smaller wings results in what we call as lesser induced drag. Induced drag is a drag that is related to the total lift produced by the wings. So with lesser induced drag, as I said before, you have less resistance to the motion of the aircraft through the air, which means you're going to be a little bit more fuel efficient.
And we can see a design in the MIT wind tunnel where, again, this original concept was formed. And we can see that double hull there, which is wider, and the very narrow wings. And certainly this is a project that has been in the works for a while, and it looks like they're going to have another 10 years or so to develop this from concept to actual implementation. Let's talk about jet lag for a moment, because most of the concern that passengers have with flying today, especially if they're flying long distances, is the jet lag. But apparently there's some new materials being developed, and in fact they've even been utilized in the new Dreamliner, the Boeing 787, and also the Airbus A350. These new materials, which are composite plastics, are allowing us to avoid some of the problems with jet lag, which are chiefly altitude sickness and dehydration. Could you explain to us what we're talking about here in terms of reducing the effects of jet lag?
Sure, and you hit the nail right on the head. When it comes to jet lag, it's basically related to feeling tired and being dehydrated. Now, with most aircraft, obviously the cruise altitude is about 35,000 feet, and 35,000 feet is an altitude at which we probably can't breathe very efficiently. So what they do is they increase the pressure inside the cabins, but they can't increase it to very high levels. So approximately the pressure is equivalent to, let's say, about 8,000 feet altitude, which is like being on a mountain resort in maybe like Rockies. So what happens is passengers within the cabin, they are going to be experiencing essentially the mountain sickness. So they're going to be a lot more tired. They're going to feel more stress and just breathing and things like that. And this gets them one of the reasons why jet lag happens. The other thing is they tend to lose a lot of moisture and essentially end up being dehydrated. With the new materials that are being used to build these aircraft, the airlines are able to maintain higher pressures within the aircraft, maybe equivalent to about 6,500 feet altitude. And with this, what happens is, if you think of traditional aircraft that are built with aluminum, metals, they are basically experiencing large pressures inside the aircraft and low pressures outside the aircraft, which means that they're going to there's going to be significant bending. But with the new materials, which are like composites, the materials are able to sustain those pressures, and so with the passengers, the comfort level increases as a consequence.
And so those materials allow the expansion and contraction, I guess, of the jet structure or the superstructure of the jet, so that, again, the bending of the aluminum isn't as severe, or the bending doesn't affect the plastics as much as it would the aluminum, I should say. And also the dehydration is less because they can keep more humidity inside the jet rather than releasing it to the outside.
That's true, yes. And with metals, obviously, the more moisture you have on the outside, the more corrosion that's going to happen, but this is not the case with composite materials. So it's not necessarily that more humidity is good inside the airplane, it is optimal humidity. So it's not more or less. So, and with composite materials, it's easier to maintain the optimal levels of humidity.
Okay, well, let's move on to supersonic jet travel. Now, we've had this in the past, even in the 1970s, they developed the Concorde jet, which was able to travel at supersonic speed, which means they broke the sound barrier and we heard the sonic boom whenever they were traveling. One of the problems with that jet, and the reason why they retired it in 2003, was because it was very noisy, it was very expensive, and there was one catastrophic crash that didn't sit well with a large percentage of the public, and so they put that aside. But now there are efforts to develop new supersonic jets that are more efficient, that are quieter, that can do the same thing that Concorde did, but with less impact on the environment. And so we have an image of one right now. It's from a company called Boom Technology. It's a supersonic jet that's supposed to travel at Mach 2.2, which means twice the sound barrier. And this would allow you to travel twice as fast. A typical flight that would take 7 hours to get from New York to London will now only take 3 hours and 15 minutes if this plane is successful. It only holds 44 passengers, so it's a smaller version of the Concorde. When we talk about supersonic jet travel, what are the challenges in terms of trying to make that jet quieter than they've been in the past?
So with the supersonic airplanes, the main challenge even with the Concorde was that you could not fly over land. So the primary destination was from London to New York and back. So with the new airplanes, some of the things that they're looking at is to reduce the noise generated by the engines beyond the sonic boom. So the sonic boom is something obviously that you're going to experience for a short period of time. And normally these airplanes are flying at really high altitude, so the sonic boom is not as significant a challenge as what the noise produced by the engines during takeoff would be. So for supersonic airplanes, the engines need to be really narrow, with the nozzles being narrow for producing the supersonic thrust. And this essentially increases the noise. So the challenge would be when you're landing at an airport or taking off from an airport, how do you minimize the noise? Beyond this, the aerodynamics plays a very important role with supersonic jets. While the design can be optimized for flight in the supersonic regime, in the subsonic regime, it becomes extremely inefficient. So if you remember the Concorde, the nose of the Concorde would actually change. It's essentially like a morphing design where the shape changes. Now, the main reason that was done was because at the subsonic regime, with the nose down, you would have a little bit more efficiency, and the supersonic, it would be efficient with the nose up. So whether the companies are evaluating morphing wing designs or new engines that can reduce the noise, that would be what we are looking at to improve the technology.
And we have a couple of other images of efforts. We're looking at one right now, which has a very narrow fuselage and a very low profile on the wings, and there's also a little blister on the tail, which is supposed to be helpful. Again, this is just a concept. It's not in development, but it's a conceptual aspect of designing supersonic jets. Why would they want a very narrow fuselage? What could be some of the reasons for that?
So one of the reasons for that is when an airplane is moving from the subsonic regime to the supersonic regime, we call that the transition as the transonic regime. And in the transonic regime, there is a new type of drag that is created. It's called as the wave drag. And the wave drag is significantly higher than the drag that occurs at the subsonic regime. And obviously, that means that your fuel efficiency is going to go down. So with a smaller profile of cross-sectional area, the effect of the wave drag can be reduced. So I am guessing that would be the reason for the more narrow design that you see in the image.
And we have one more, and that's an updated supersonic design or concept by Lockheed Martin. They're experimenting with putting an engine on top and one engine below. Maybe they're just trying something out. So I guess the important thing when we look at these images is to realize these are concepts. They're not works in progress, they're just concepts. So developing concepts and testing them in the wind tunnel, that's pretty common for engineers.
Yes, and also, with the improvement in technology, especially in simulation, right now, obviously we depend on wind tunnels for the final testing, but getting to evaluate the design in the preliminary stage, we now have computational tools, we call it computational fluid dynamics, that allows you to, test radical designs and not really invest too much money into it. So you're able to evaluate what an engine above and below the wing is going to do without having to worry too much about the cost of actually testing it.
Well, we've run out of time in this first segment, so we'll come back and we'll continue this conversation. And when we do come back, we'll talk about robotics and some of the exciting new developments occurring in the field of robotics. Stay tuned.
Ever heard of the world's most amazing toy? Uber sticks? I mean, check it out. The Eiffel Tower, the Golden Gate Bridge, cars, and robots are all amazing feats created by mechanical engineers. You could become a part of this creative field with a degree from Cal State Long Beach.
Welcome back to Talking Points. I'm Dave Kelly. My guest today is Dr. Praveen Shankar. Praveen, in the first half, we talked about aviation and some of the new developments in engineering technology dealing with aircraft. But now we're going to talk about robotics and what's happening with robots, the implementation of automation and robots, and how these devices can now talk to one another or communicate with one another. Let's talk about that for a moment. How do these robots talk to each other? And let's start with the self-driving cars, because in order for the self-driving car concept to work in terms of being implemented on a mass scale, those vehicles are going to have to be able to communicate with other vehicles. How does that work?
So with self-driving cars, we already have self-driving cars that are operational. The primary way that they operate is they have onboard sensors that is, basically perceiving the environment and making decisions based on that. And it is exactly similar to how we drive cars. I mean, it's just that the sensors that we use are slightly different from the sensors that these cars use. And also our response times are certainly different, and our brain probably is processing this data at much more faster rates, and it's able to adapt quite well. With the communication between cars, what is going to add is an additional level of information that the car can use to make a decision. Now, when we talk about humans driving cars, of course, we're using our eyes and our ears to a certain extent, but we're not talking to each other. So it's actually using communication between cars is a novel idea. So is this going to help or not help? That's a question that we'll probably answer in a few years. But I think the more information that the car has to make a decision, it would be better.
I've actually, back to aviation for just a moment, I've heard that autopilot is actually safer than having pilots operating jets, at least in the air. Now, when you get to the landing, then you want the pilots to be involved, of course. But we have many years of experience now with autopilot. Right. It works.
Yes, it does. And again, when it comes to the autopilot, the basic idea is that there is a fixed task that needs to be executed, and the autopilot maintains that task. And the main reason why we believe that it is safer is because the autopilot does not get fatigued as a pilot would, especially on long flights.
Doesn't fall asleep.
Doesn't fall asleep. With the self-driving car technology that is coming up, it's not just maintaining a particular task, but responding to certain situations which may be changing very quickly, highly dynamic. So yes, I do believe that autopilot knowledge that we have from airplanes is going to help, but there's significantly more development necessary for true self-driving cars to operate within our environment.
Well, let's transition to a project that you're working on and that you're researching right now, and that is assembly line robots who are able to talk to one another on the assembly line and to actually make changes based on situational occurrences. Right. What's involved with that technology?
So the main reason why I was motivated to pursue that project was I wanted to look at the self-driving car technology and develop any needed expertise for that in a constrained environment. So one of the things that I thought about was if you go to let's say a manufacturing facility, let's say a car assembly plant, you have these robots that are set in a serial position, that is one after the other, and the car moves from one place to other. So the first robot maybe welds the doors to the car, maybe the second robot assembles some other part to the car. So I wanted to see if we can reduce the space utilization by all these robots and do this manufacturing operation in a smaller environment where the robots have the possibility of interacting with each other or becoming obstacles to each other. So any technology that I develop in this area could be applicable to self-driving cars as well, because you have their cars which are robots that are interacting with each other. And there's several sub-technologies that need to be developed. One of the things is communication. When you talk about two robots that are communicating to do a task, we are normally talking about wireless technology, which means there's a possibility of delays within that communication. So how does that affect the performance of the robot? Then there is sensing technology. What kind of sensors are we going to use? Are we going to use sensors on board the cars, or are we going to have sensors on the road? So environmental sensors that might play a role. How are you going to plan the motion of the robot? Because now you're talking about robots that can interfere with each other, so which means obstacle avoidance becomes a big deal. Same thing can be talked about self-driving cars.
And so actually on the assembly line where these robots are putting cars together, they're now doing multiple tasks. Each robot will do a multiple task based on what another robot next to it may be doing, or what the robot before it was supposed to be doing. Right. And as you're talking about the situational awareness, it means one robot needs to know if the other robot is doing its job properly, and if not, it needs to adjust in order to accommodate for that until that first robot can get its act together, so to speak.
Right.
So in that case, we're talking about essentially dynamic learning. Let's talk about dynamic learning. What do you want the robots to do?
So, in the assembly process, right? I mean, let's assume that there are 4 parts that go into an assembly, and one of the robots is unable to place, let's say, part A on the complete structure. then what does the second robot do? Will it go ahead and place its own part, or will it adapt to the situation and maybe back off? So there might be different solutions to this problem. Maybe there is a solution where robot 2 can compensate for the error caused by robot 1. So, but for this, the robot has to be able to learn in real time and basically adjust to the situation.
And so that's what we're talking about, dynamic learning, and then building upon that database of knowledge in that robot system so that they're all at a point where they're in a kind of a choreography and a synchronized choreography, and also helping each other out, like humans might do on a production line.
And dynamic learning, a popular term for this is actually machine learning. So machine learning has become a huge deal now for several things. I mean, we even have machine learning in our homes. Like, for example, the smart home systems that we use, they learn, continuously learn to adapt to the way you behave around it. It's the same thing with these robots as well. Do they learn to adapt to the environment? And this goes down the road of artificial intelligence and so on, and we have heard a lot about this in the media.
Well, if you're developing this line of robots that can communicate with one another, can help each other out, can figure out what the other robot is doing, and then maybe pick up the pieces if it needs to, when we talk about that and developing that in a lab like yours, you're going to need other engineers with a variety of areas of expertise. How many engineers does it take, and what kinds of expertise do they need?
That's a very good question. Well, from an expertise perspective, I have a lab, we call it a Collaborative Autonomous Systems Laboratory, and we are trying to do these kind of collaborative robotics. But I do collaborate with other faculty from the department, like I have collaborations with electrical engineering, computer science, and within the lab itself, the students that participate in these research projects, they are very diverse. I have students who are mechanical engineers, aerospace engineers, electrical engineers, computer scientists, and computer engineers, and they work with each other because as a sum total, they have the knowledge to solve the problem, but individually they may not have the ability to pursue this.
Well, if I'm an electrical engineer, how much do I need to know about mechanical engineering? And if I'm a mechanical engineer, how much do I need to know about computer science in order to make this all work together?
So one thing is, let's assume that each of the students are given a module to develop. Now, these modules cannot be developed independent of the other modules. So you must have some knowledge of how the other module affects your own module, and this is why a lot of the companies, the big companies which are developing products, place so much importance on system integration. So while a student may not need to know the exact details of what is happening with another person's area of research or area of work, they need to know how it integrates into their system. So yes, they need to have some knowledge about it, but it doesn't mean that they need to have complete expertise in that area.
So they don't have to be an expert, but they have to have some working knowledge of what that other contribution is to the project.
Yes.
We're talking about students now. In your research lab, which you refer to as the Collaborative Autonomous Systems Laboratory, you have students there that are actually volunteering their time. Why are they volunteering their time, and what's in it for them?
So one of the most important things that the students are looking forward to is getting a job, right? And how do you get a job? Well, you need to differentiate yourself from all the competition. So what the students want to do is, beyond what they learn in the classroom, they want to get some experience on things that is going to be dear to the industry. So hands-on experience is always very well appreciated when a student applies for a job. In addition to that, the students, they volunteer because it gives them a chance to explore new things. So, in the classroom, they pretty much follow the lecture and answer the questions and, carry out the assignments that are given by the instructor. In the lab, they're able to think beyond that, and maybe they have some new ideas that they want to implement, and this basically motivates them to push their career further.
When you're developing a project or working on a project like this, what is interesting to you? How do you pick the projects or the proposals that you decide to work on? What stimulates your interest?
So, obviously the information that I get from, industry, we do have a lot of collaborations with industry, and sometimes they tell me, here is a challenge that we are working on. Would this be something that you are interested in pursuing? There are also, federal organizations like NSF, NASA, and Department of Defense, which have particular challenges that they want to address. So these are things that sort of give me an idea of how to push my research. Beyond that, I have an expertise in control systems and in robotics. So I come up with some of the ideas on our own based on what I think could be the future. We also have students participating in competitions, engineering competitions. Now, these engineering competitions are very design oriented, so there's really not much research involved in it. But sometimes when you're addressing a particular design topic, underlying that there could be some research that could improve your design. So those are things that we get ideas from as well. But when an idea comes to me, obviously I like the novelty of it. I mean, it's always exciting to do something that nobody has done before. But also I look at how grounded it is in the fundamentals. So as long as it's grounded in fundamentals and it is sufficiently novel to pursue, I think that would be something that I'd be interested in taking on.
Well, we just have a couple of minutes left. I wanted to ask you about the future. What kinds of areas of engineering are going to see the most growth, do you think, in the next few years, up to the next 20 years?
So one of the things that I feel is going to change the way our machines operate is the artificial intelligence. I mean, we have new algorithms coming up, new sensing that is feeding into these artificial intelligent algorithms. So as a whole, machines that are able to think for themselves and act based on the situation, that's going to be very significant 20 years from now.
And we've just about run out of time. I'll give you the last word here. So when we look back, 20 years hence, we look back at today, what are we going to say? It was all about artificial intelligence?
I would like to say that, but I'm sure there are a lot of engineers who would disagree with me. There are technologies and in development for every sub-area of engineering. For example, materials is a huge area where we are getting, flexible displays and things like that. So yes, I would like to say artificial intelligence, but I'm sure there will be a lot of people who will disagree with me.
And on that note, we'll have to conclude the program. Thank you for being here today.
Thank you.
And thank you for joining us for this edition of Talking Points. Be sure to join us again soon for the next episode. Until then, I'm Dave Kelly. Have a nice day.